You just email it to me. Probably.
Yeah. All right. I guess I'll go ahead and begin unless there's anything you want to say.
I mean, we have Upstat. You've been seeing that. It's like a, statistics in machine learning conference. It should be cool. Luckily, it's at RIT at WU Bar. Looking in to see if I can burn some data side funding covering the student that we could use for. Yeah, stay tuned.
Yes. Oh, I can plug in Great Lake Security Day, which is happening immediately before Upstat. So if you have any interest in security, you'll see at least some of the posters there will include AI or data analytics applied to various security problems. If nothing else, you'll see me here or there, plus some of the other deep learning folks from my lab. Okay. Well, you can see my talk will be going over a number of different fingerprinting techniques that we can apply to network traffic. This is largely going to cover pretty much all of the different ideas and concepts I've played around with the 4 years that I've been in this PhD program. So who am I? I'm a 4th year PhD student. My advisor is Dr. Matthew Wright. My research mostly is focused on applying various deep learning algorithms to network traffic, and in particular, dealing with and oftentimes specifically breaking the privacy that certain tools and techniques can provide using fun little deep learning classification attacks. So I also did my undergraduate here at RIT. I graduated in 2019, and so this is now my 8th year coming up to it being here in Rochester at RIT proper. I am at this point looking forward to moving on in the next year or two and finishing up this PhD and getting out of the crappy weather that is Rochester. I've got over the last, what is this, like 5 years, a number of different papers that have my name on it. Really, the 2 key papers that I was a main contributor to is my first paper back when I was an undergrad, and very recently a large kind of analysis of website fingerprinting defenses. This presentation is going to be touching on a lot of content from many of these different papers, but not all. That would be far too much to cover. So for a general outline of what I want to cover today, I'm going to be focusing on fingerprinting network traffic. What I want to look at first is this problem of what we call website fingerprinting. Specifically website fingerprinting on the Tor anonymity system, and I'll talk about more about that in the next slides. In addition to that, there's another related problem called traffic correlation, which can tie right back into the Tor problem of preserving or breaking the privacy guarantees that Tor can provide. And we just recently finished up a project on that. And we are now taking what we learned from that project and applying it to a new security problem, but kind of in the reverse. Rather than breaking people's privacy, we are hopefully going to be using this to defend against, or at least detect, attacks in real systems. And then we will almost certainly not get to this content, but I've done some work with specifically trying to identify voice commands that you send to your smart assistant through the network traffic. It's very much related to same type of problem of website fingerprinting, but now on smart home systems. I'm pretty sure we will have plenty of content to cover in just those two bullets. So in addition to this stuff, which I mostly do network traffic related content, My lab is pretty diverse in that, in addition to network traffic, we've got groups that do a lot of deep fake work. And if there's time at the end, I can plug them in a bit because they will be hiring for summer researchers in the next probably month. And separate from, still in the security domain, but separate from network traffic, we are finally getting around to playing around with applying deep learning to various malware detection and malware related problems. I'm kind of adjacent to that, but I will not be discussing that topic further in these slides. Something I want to focus on really quick is two particular projects. I just want to say that we do have funding for one of the current traffic correlation projects we're running. So if you find any of this network traffic stuff interesting, you should send me your resume or any information, and I can keep that on hand when we are looking for people. And then separate for that if you find deepfakes interesting and want to work on the deepfakes project, do the same. And I can forward that information over to that group, and perhaps give you a leg up when they are hiring in the next month. So moving on to the actual content of the talk, we got to start by defining what this Tor system is, and I'll quickly go over what it's a general idea of internet anonymity. So traditionally, when you are doing any type of communications on the network, like web, you are directly contacting some end server. In our problems, we're going to be looking at websites in particular. When you directly connect to a website, that website knows your IP address. Anybody who is listening on the link, like NSA sitting on backbone routing networks, for example, they're going to be able to directly connect your IP to whatever IP it is you're visiting and communicating with. Now, there are many ways or many reasons why you might not want that to happen. There's benign or like good reasons to do so, such as many journalists need to protect themselves from like Chinese government from spying on them. But you can also use this for crime and whatnot. So one easy way to try to prevent some of that privacy leakage is through relaying your traffic instead of directly to the endpoint through a VPN, for example. VPNs then have their own issue where if your VPN is compromised, it's still not a perfect protection. So we can extend on that a little bit further with this concept of Tor, which now, instead of effectively relaying your traffic through one node between you and your endpoint, you relay it through multiple systems so that any one system doesn't get the full perspective of what this network connection is. So like the entry node can only see the client and this middle node, which neither of that provides enough information to really get that full connection of matching the client with the website that they're visiting. So in this, what we call the website fingerprinting attack, we are looking at this particular problem from a certain perspective. Now we imagine that we have an attacker that is able to listen on one link, and we'll look particularly at this link directly by the client. So they're eavesdropping on the connection between the client and the start of the core network. But you could also, apply the same circumstance with someone sniffing on VPN traffic, for example. And the way this attack works is the adversary is going to collect a bunch of traffic samples and use those traffic samples to train up a classification system that they can use to try to make predictions as what websites you visited based on the traffic that got generated during that visit. So to reiterate, the goal here is for this adversary to link the client with the website or endpoint that they're communicating with.
So what features does it use for classification? Was it looking at?
Yes, I'll jump right to that. So we'll, I don't know how many of you have taken a look at like raw Wireshark or PCAP, like network traffic captures, but this is kind of what it looks like. So what the attacker has on hand is just this sequence of packets being sent and received on the network. And I've taken a screenshot here of what is just a standard HTTPS connection that is not protected by VPN or Tor. So you can see some information in the actual data of the packet. So for example, you can look at the DNS request and see that, oh, I was loading Amazon in this connection. You wouldn't know what I'm specifically looking at on Amazon, but from the unencrypted data here, you could get that much. In our circumstance, we can, since we're feeding our data through Tor or a VPN, all of the data here is kind of blocked. We're limited then to really only being able to look at like the metadata of the packets. So specifically looking at the direction of each packet, like is it going to the endpoint, is it going back to the client? What size are the packets? And then what time did the packet get sent or received? But just from that simple metadata, you can really characterize any website based on patterns that exist in just that sequence of simple information. So here's a brief look at a comparison of 3 websites. I don't know what that end website is. But you can see how significantly different just graphing these 2 different data sequences in either the perspective of just packet timing or packet sizes, where for these particular sites here, you wouldn't need a machine learning algorithm to really even classify this. It's so trivial to separate. But you'll find that when you scale this up to like the whole world of internet websites, you start to have far more overlap between sites of similar size, and there's oftentimes a lot of variance within a single website in terms of what the traffic might look like between multiple visits. So what I then now want to look at is I'm going to skip over some of the older, less, I think, exciting and sexy machine learning stuff. And we're going to jump straight to how do we kind of formulate this problem such that we can feed this into a deep learning system and have the deep learning system learn just from these raw metadata traffic sequences. So basically what I want to show off here is there are a couple different ways you can kind of present and frame the raw traffic data. The most basic way that the kind of literature started with was just looking at the directionality of packets in the sequence and treating this as a stream of packet directions. But this is pretty naive, and you're leaving a lot of information on the table, like packet timing, to incorporate. You can also then look at this and try to capture more patterns in the actual traffic sequence itself. So if we take the packet directions and then sum them over each step, we get something that is like that graph we looked at just in the previous slide. And this is something that, if you graph this, you could probably distinguish between websites yourself. And this could hypothetically be a little bit, if nothing else, more understandable why a machine learning or a deep learning algorithm can learn from a traffic sequence like this. We can also start to incorporate some timing information to this. So a common method in literature is just to multiply the raw timestamp by the direction, or represent the traffic sequence as a sequence of time differences between each packet arriving, and then multiplying this by the direction to include that directional data. Now there's no reason you can't use all of these sequences together, but interestingly enough, very few of the older literature did that. But you can kind of basically map these things into a multi-channel data representation and feed all that data in. So the very early deep learning applications in website fingerprinting use the packet direction sequence, and what this model, what we call deep fingerprinting, looked at is very simple. You just take your big data set. In their case, we had 1,000 samples for 95 different websites, so 1,000 samples per website. And we trained just a simple 1D CNN on the packet direction sequences. And so if you're at all unfamiliar with CNNs, it's I think pretty simple. You can kind of break down a CNN into the convolutional sequence, which is reducing the input sequence into effectively a series of feature maps, where the 1D CNN can identify broader abstract features automatically based on the training data, and after doing this kind of automated feature extraction, we can feed it through a simple MLP to get out a prediction or classification.
We went over CNNs, they should know.
Yeah, I hope so. It is like the simplest. And despite its simplicity, it performs really well in the smaller 95 site case, achieving up to 98% accuracy just based on the packet directions, not even using the more kind of information-rich packet information. And the architecture that we use with this deep fingerprinting attack is also very simple. I don't know how much you went into CNNs, but you've probably seen things like ResNet, which uses residual connections to have deeper networks, as well as many different new training strategies that convolutional networks like to use nowadays. This uses the very basic convolutions, some dropout, and some batch norm, and that's the level of sophistication that we include in this network, and it's still the benchmark network to use today, which is kind of frustrating because I'll talk about at least some of my attempts to apply transformers to website fingerprinting and how small the performance benefits are in these circumstances. Now let's see. So one downside of using deep learning and requiring a more kind of longer training process to teach the model how to pluck out useful features automatically from the raw traffic sequence is that it requires a fair bit of data to get the model doing well. In our case, with the deep fingerprinting model, around 1,000 samples is what we needed to hit those performance numbers. And unlike, say, images, network websites have this problem where websites tend to change, and the properties that can characterize a website or the network traffic produced from visiting that website will change over time as the website itself changes, or protocol changes. I think during our research, they have, since we've seen a shift towards I think it's HTTP 2 to the quick protocol, which really significantly changes the way websites are loaded, which impacts these models that get trained up on this data. So it's really unlike image and the vision domain, where you can train a vision model, and that vision model is still going to do what it does on samples of cats, just as it did, 100 years down the line, unless cats fundamentally change in the way they look. And, yeah. With our website problem as well, because of this data staleness, to actually be able to apply like a website fingerprinting attack like this in practice, you would need to constantly collect new samples of any website that you're trying to identify. And that gets pretty expensive when you need to, like it takes 60 to 90 to 120 seconds to load and save the data of any given website. Do that, 1,000 times for 1,000 or 100,000 different websites. It's just become kind of impractical, at least for the majority of potential attackers, to do this type of collection.
Why does it take that long to get your data?
So one issue is Tor is just really slow. So that is part of the problem. There's also when using Tor, you'll oftentimes find that if the endpoint of your Tor network is sitting in like a location that was blocked by the website, you'll have to recycle your Tor circuit and establish new circuit of relays, and that can lead to a lot of bad data that you have to filter out and collect more of. Yeah, it's just expensive. Like someone like the NSA could do it if they cared enough and thought they could actually apply this in practical benefit. But even then, they're going to look like it's always better to reduce the amount of compute costs that you have to spend to do something. So as a response, there's been a number of different proposals in trying to reduce the number of samples needed to perform these website fingerprinting attacks. Two of these three here, I worked on fingerprinting, which uses a contrastive learning of a type to try to pre-train on old data and use that pre-trained model with kind of old data features to bootstrap the learning process on a few new samples that are fresher. And then we have this Gandalf attack, which instead took a very different approach, where we used GANs to basically kind of act as a data augmentation or multitask learning strategy. I think I'll probably end up skipping through these Gandalf slides and moving on to traffic correlation, because I think it is more interesting and it is where we have money to hire people. So I do want to
use some the GANs to like create some sort of synthetic data.
Kind of. So it's a little bit more complex than that. I'm going to assume that you generally have an idea of what a GAN is. But the idea with using GANs for semi-supervised learning, which so it's like you have some labeled data, but a lot more unlabeled data that you want to use for some practical benefit. You can get your discriminator, like the discriminator / classifier piece of this broader model to not only configure it so it's not only trying to target making labeled predictions, but also need to distinguish between real unlabeled samples or fake samples generated by the generator adversarially trained model. The idea here is by having this kind of like combativeness between these two models, you can kind of force the discriminator to learn better and more like robust features from the data, which can kind of help improve performance, especially in like testing when you're needing to generalize on a bunch of unseen samples. The problem with using GANs is GANs kind of suck and are really inconsistent to train, especially when you're slapping on this whole other component where the discriminator is not only learning between real and fake, but also it's learning to classify into separate subcategories. So we oftentimes would find that the discriminator would outperform the generator if you made the discriminator too good, and at the same time, you need your discriminator to be pretty damn good to be useful for classification.
So that aperture component was hard to say. Ideally, your models are kind of like evenly matched.
Yeah, you need your generator and discriminator to be matched evenly, but at the same time, when you're applying this technique and like a real classification attack, you need that discriminator to be as good as it can be at the end. So it's a really weird thing to balance. We were able to get and publish a paper where we could improve classification performance by a bit when we had under 50 examples. But there's really, I think, still quite a bit that can be improved on that certain direction. And my solution to attempt to do that has been with transformers. I could probably spend, if I wanted to properly go into transformers, half an hour going over the various components. So to give a very quick overview, transformers are basically composed of two different blocks, the encoder and the decoder. We will, for the purposes of any type of classification type of problem, we pretty much ignore decoder half and just look at what is a more kind of traditional like feed-forward network without any weird interconnections between different submodels. Transformers have a couple key elements to them. They are the multi-headed attention, which is this kind of important key piece that is doing spatial mixing across the entire sequence of data. Then some other pieces, as well as residual network connections and positional embeddings. Those are all just details. So looks like I already did good. So jumping over to the core applications that I want to inspired by. Is transformers have done really well in not just natural language processing, but are state of the art in a number of different vision domains and vision classification tasks. This is very similar to the direction we went originally with website fingerprinting, which is using many of these vision-based classification models, tuning them and modifying them to fit well with our website fingerprinting approach and doing exceptionally well. So what I've focused looking at is this transformers for vision model, which is a really interesting approach. And to quickly go over it, to do classification with a transformer, which transformers are a little bit interesting in that they will spit out not just a single prediction typically at the end, but rather a sequence of outputs that you can train to do whatever it is that you want it to do. So the standard way to now modify this to apply it for vision tasks is to chop up your image into kind of separate tokens, map them into an embedding space like it's natural language, for example. Feed that through your transformer classifier, and then stick a initial class token at the very front to use as your kind of final outputs for the classification of that image, or whatever other tasks you want your network to do.
So does multi-headed come from if you have multiple like NLPs at the end trying to do classification?
Kind of. Let me see if I do have slides here that might help explain it a bit. But this isn't going to help all that much. So, well, I think transformers are super interesting, but the multi-headed is more related to the attention module component. Basically, the multi-heads are kind of like having multiple kernels in the convolutional layer. They are like effectively different attention mappings produced in parallel for that particular layer.
And attention is like a kind of a feature importance, or like what it's paying attention to.
Yeah. Yeah, I think it would take me, like I mentioned before, quite a while to go into attention, and what really is happening with attention is this idea of spatially mixing information across the entire global sequence of data, your natural language. Yeah. But so this does have a number of properties, and one is that global element of learning that these transformers are possibly capable of. And so this system is oftentimes used for image by all the big guys, Google, Microsoft, Facebook. And they get some really good performance, and I've been basing my model based on this. Now, the other key element that is interesting, and I realized I didn't have a very good slide that demonstrates this, but one thing that's missing from this figure on the right here is while each of these patches would map out to an individual output relating to that patch. So for classification, there's only one output that we care about, and it's this very first token that we train to include the classification information. But that leaves this whole other sequence of outputs that are kind of more or less ignored. In language, with the BERT model, what you see these used for is for basically like richer feature representation. So you can use these for other downstream tasks. But one other thing that you can do with those outputs is you can train them to do a little bit of different things. In particular, one very popular way to train them is to train them to try to reproduce unseen or masked out portions of an input. And in this way, try to get your network to learn really rich understandings of the data, so that they're able to reproduce as closely as possible these unknown masked out pieces. And then you can use that pre-trained model for other downstream tasks. And in my case, the goal is to take this kind of reconstruction, self-supervised learning approach, applied to pre-train like a nice big network model, then fine-tune on small amounts of samples for whatever class or website that I want to detect. At the moment, it's going somewhere, but it's certainly not producing especially exciting results for the amount of compute that goes into training these damn massive transformers. And one key, I think, appeal for a lot of the big players like Google and Microsoft is these transformers are great at scaling with the data sets that you have. I don't have millions of traffic samples to work with, just about 500,000. So I'm probably not seeing the full scaling potential. So I will have enough time to go over the second piece of internet anonymity. So we looked at website fingerprinting, and in website fingerprinting, we've got this adversary that's only on the left, or I guess, yeah, it's left for you guys too, side of the connection, and there he's capturing traffic samples and trying to predict based on patterns in that traffic and known examples of those patterns in like a pre-training data set. So we can imagine instead a more powerful adversary that is not only capturing on one side, but is capturing both ends of your VPN or your Tor network. Because if they're able to do this, this opens up another type of attack that they can do. So if they've collected all the samples that go into the network and all the samples that they are spitting out, they can try to match up the in samples and the out samples. And when they find a match between those two different sets, then you can kind of definitively say that this client and this website is the two that we're talking with each other. There are some more difficulties here. It's not as simple as just having two traffic sequences that look more or less identical because they contain the same content. Because the actual application protocols that are being used on the two different sides are different. One is encapsulated in some Tor protocol packaging, and the other is in your standard HTTP or whatever the protocol that you're using for the endpoint. And in addition to that, you also have packetization changing as they get repacketized at every hop of the network. There are timing differences between the two as the whole multi-hop sequence leads to added latency. So your correlation system that you build to kind of match between these two different sets has to be fairly robust to noise. And that's where potentially using deep learning comes in, which is what we did with this contrastive learning based approach with deep learning. So we kind of already went over the general concepts of trying to match up the two ends of the flows. One issue that we have when we attempt to do this is your two sets at both your left and right side are going to be pretty large. If in like our toy system, we imagine that, okay, maybe the Tor is only servicing 1,000 different users with different connections on both ends. You're then trying to match 1,000 set of inflows and 1,000 set of outflows. And for any given inflow, one of the 1,000 will match up. And when you find that, you can identify where that user's going. Problem is that we don't just have 1,000 users in practice. Oftentimes it scales up to far greater. And this is what we call this problem, the base rate, where the frequency of correct matches is way lower than the total number of possible matches. So your classifier not only needs to be good, but really good. Otherwise, any false positive or incorrect guess is going to easily outnumber the number of correct predictions, because the number of correct predictions are so far and few even available. There's a little bit of an example. So now the way we try to train a network to do this correlation with as little error as possible is we use this triplet loss contrastive learning approach, where we train these deep learning networks to try to basically reduce the distance between in a embedding space between known pairs and then increase the distance between unknown pairs. The way this kind of goes about is what you have for any kind of sets of data is we divide our samples into anchor, positive, and negative samples. A anchor sample is like the key sample that you're comparing other samples to. A positive sample is a sample that correlates with that anchor sample, and then a negative sample is one that doesn't correlate. So we want to train a network to make the distance between your anchor and your positive samples be really close, and the distance between your anchor and negative high. And now, because we have two different sets of data, the way we went about that is kind of interesting in that we use two different networks for the inflows and the outflows. So the models are more capable of handling the specific network properties of like the Tor protocol versus the HTTP protocol. And to try to reduce the failure rate further, we can take this idea of what we call amplification, which is this: rather than trying to predict the entire, if the entire sequence correlates across like a whole 30-second say web page load, we can now, instead of imagining trying to do a single prediction, which is either going to be a correct one or a wrong prediction, breaking it up into a bunch of mini predictions. And if enough of those mini predictions indicate that these things are correlated, then that's when we can decide that the full connection is a correctly correlated sample. You can kind of think of it like the idea of flipping a coin. If like heads is true and tails is a failure case, the more times you flip, the more likely you're going to converge to eventually a failure. So we can reduce the number of false positives by being very sensitive to any piece or window of the network traffic that doesn't correlate.
Do you use the same features on each piece of that traffic?
Yeah, so we will use the same model to basically ingest each subsection of the trace. I think I've got a good way. So like we break up our trace into a bunch of overlapping windows. So you've got, like, let's say you have the traffic sequence of 1,000 packets. You can chunk this into like 5 200 packet windows, or I guess 10 200 packet overlapping windows. And for each of those 10 windows, we take the inflow and like the candidate outflow that might be matching, feed it into the deep learning models, get the embedding values that are produced. And if they're very close to each other, then for that window, we say that they're correlated. And you do that for every one of the windows. And if you find that the vast majority of the windows are correlated, or all of the windows are correlated ideally, then we see the full sequence is correlated. But if only like one, or I think the threshold that we picked was specifically 2 of, I think, 8 windows don't correlate, then we consider the thing uncorrelated and don't give a positive signal for the purpose of the classification. And what this really does, here we go. It's 9 out of, if 9 out of the 11 windows are indicated as correlated, then we say the full sequences. But if just 2, or if 3 of the windows don't correlate, then we throw out the whole system, or the whole pairing, and say that the pairs are no good. And what this really helps with are traffic sequences that are very similar to each other. And you'll see in practice a lot of traffic. So for example, like 2 users are both visiting Amazon at the same time, the separate users' connections are not going to be, shouldn't be correlated to each other. But if the contents that they're both visiting at the same time are very similar, then many of those windows would correlate, but not all of them, as you would expect some differences in terms of the timing noise that got added, and little small distinctions between them. So if you can pick out enough of those small distinctions to flip it, that's enough to get a little bit better performance like constrained environments. And then when you scale this up in cases where your base rate is as low as it is, that leads to a huge performance benefit in terms of reducing that false positive rate when compared to the more naive approach of trying to ingest the entire sequence all at once. Now, moving on to what we can use the same concept for, but rather than attacking for people that use Tor, we can use this for trying to detect attacks in a network. So I'll try to really quickly cover the basic idea. So let's say you have some company network with a number of different machines. You've got some attacker who is trying to attack this network and will, in theory, eventually try to extract out some valuable information on the network. We've got this gold, nice, juicy data that attacker wants. In a well-designed network environment, that juicy data is going to be behind multiple firewalls and multiple subnetworks to try to protect it from a malicious attacker that's going to try to get and compromise all the way into that more sensitive portion of the network. So for an attacker to do this, they're going to need to compromise multiple hosts along the way, each a little bit closer to that well-protected network until they're able to eventually route their connection through a number of different compromised machines into increasingly sensitive segments of the network. And so this leads us as a defender an opportunity to potentially identify such a attack, which we call a pivoting attack. If we are capturing at many different points along our network, we can try to use this correlation idea to link related traffic samples that might indicate that somebody has routed a connection through many different hops in your network. So like, for example, if in this case, if you find that the connection between there's a connection between host 1 and 2 and 3 and 5, just the money location, have very likely correlated traffic, then it's very likely that somebody has created a connection that routes all the way through both pieces, and it might be an indicator that someone's like exfiltrating data through your network. There are a number of different ways you can go about doing correlation to try to map and identify these attacks. You can try to correlate multiple places in the network or just along hosts. This can all be very helpful to improve basically the accuracy of how well you're able to detect and separate the real stepping stone attacks versus somebody just say doing an SSH connection through multiple machines because they're lazy to reset up new connections. And there are various different techniques out there. We divide them into 3 different categories. And we recently got a grant through that attempts to, we propose various deep learning strategies to try to do detection at these various different perspectives. So for one, we've got a proposal out there that we will be applying that traffic correlation broad framework with joint types of data to correlate at the host level, and then we can combine that information with like the number of hops, the number of timing characteristics to try to detect if there is like a large number of connections that the traffic chain is being routed through. So that's another strong indicator that this is more likely an anomalous or malicious sample. And then there's this separate idea of embedding fingerprintable like timing delays or certain characteristics to sensitive data sources, or on sensitive machines like databases in networks, and then trying to somewhere else identify those watermarks in the network traffic patterns. And there are a number of ways to do all these different things with fun different types of deep learning networks like GANs or diffusion networks. At the moment, for stepping stone detection, we are at the data collection phase, but we will soon be moving on to experimenting with these various different deep learning topics to try to solve these separate different sub-problems. So I think I have managed to fill most of the time. The only thing I didn't cover that I do also have a separate ongoing project on, and that's the idea of using these very similar website classification techniques, but applying it to network traffic produced from voice commands. And we've got some data, and we're doing another new data collection for a larger set of voice command data. Yeah, the idea is to try to classify based on the network traffic what type of command, or what questions you're asking your Google Assistant or Alexa Assistant. It's not a super sensitive attack. So I don't know what type of attacker really cares to spend the amount of effort required to do it. Like NSA sure as hell doesn't care. They'll just buy the data straight from Amazon or Google. But it's an interesting little research problem. Yeah, exactly. You're fine. I think we're just about ending up now.
There's a thing.
Yeah.
We're in here for a few more minutes.
Okay.
Yeah. The last thing I wanted to plug was this deepfake project that the students in my lab are working on. If you're not familiar with the idea of deepfakes, then you should probably pay more attention to current events and various AI generation tools. It's pretty impressive at the amount of convincing fakes that can be generated at this point. The other group in my lab is working on not just detecting these deep fakes in like single images, but also stringing that along into detecting deep fakes across full videos, and very specifically building applications and kind of holistic kind of deep fake detection interfaces that someone who's non-technical can understand and have a lot of confidence in. So they've been working on a lot of different usability kind of frameworks and studies to not just build good detectors, but build good detectors that are explainable, that use various different deep learning explanation techniques to try to provide some more reasoning as why a model has flagged a certain file for possible fakeness. And if you find that at all interesting, you can certainly send them an email, send me an email, and I can get them your information. Because we are probably going to have funding over the summer to hire some students to work on some research projects for that. Okay. No, that was a whole hell of a lot to ingest. Does anyone have any other like questions on any of these different projects? Actually, I can go ahead and need to stop sharing. Or otherwise we can, end it. Yes. All right, well, thank you all